Welcome to the beginning of Unit 4, Thermochemistry. We're going to do this the same way we have been doing it. So we'll start with a short set of learning targets, and then when you're finished with your part, you can start the video again, and I'll give you some additional information. So your learning targets are here. You may want to stop the video so that you can go skim for what you need to write down. Remember to leave lots of space so that you can add additional things as you watch the video after you restart it. I will let you pause it and I'll see you in a minute. Okay, welcome back. Here we go. So in thermochemistry, there's lots of different things that we can look at, and the beginning of this unit is already going to feel a little bit like a mishmash of stuff that we're putting together, but there's lots of terminology that you need to know before you get started so that as we start to work with it, you can keep things straight. So one of the things that we do a lot of is something called calorimetry, and this is a picture of a calorimeter, but it's a really good example of how we have to separate what's happening from the surroundings. And we have to consider that especially heat transfer happens all the time between the system, which is often your chemical reaction, and the surroundings. And so this is a perfect example of a way to kind of keep this straight. So you learned in what you read that we could be really obnoxious about this and say that if the system is the ice melting, that technically the cup that it's in and the table that the cup's on and the air that's around it and all of those things are the surroundings. But we definitely want to make sure that we are talking about the relevant surroundings as we do this. So some things that you have to remember is that if I have something dissolving in water, the water itself is not the stuff. It's not the system, it's the surroundings. All right, so I really like this picture that I stole because it says that the system is dissolved in the water, which makes the water surroundings. Okay, and that's something that's really hard to keep straight, is that if you're dissolving something in water, you want to picture that the water is a piece of what's happening there, but the water is actually going to either provide energy to the process of dissolving or remove energy, receive energy from the process of dissolving. And so the water is not really the system, the water is the surroundings, which means that only the chemical that's dissolving in the water is the system. The water is the surroundings, the thermometer is the surroundings, the styrofoam cup is the surroundings. In this case, the air that touches the water is the surroundings. And so this is a really important distinction. And it's going to be confusing as we work with calorimetry. The one thing that you have to think about is that the thermometer especially is always a part of the surroundings. And the reason that we care so much is because if the system gives off heat, it gives heat to the surroundings. So the perspective that we have when we're taking data will almost always be from the thermometer or from the fact that you are holding the cup. And so your hands are the surroundings. And if your hands feel warmth coming off of what you're holding, or if the thermometer rises, then it's absorbing energy from the system. And that means that the system is giving off energy. That one's pretty easy, but when we go the other direction and you feel something get cold, our terminology in real life doesn't do us any favors when we say things like, I'm getting cold, because really we're not getting cold, we are losing heat. And so if we're feeling something and holding something and it feels cold to us, that means that it's absorbing heat from us, which would mean that the system is absorbing heat from the surroundings if the thermometer's mercury goes down. And so just always try to keep this straight. It's going to confuse you and we'll keep talking about it, but I wanted to introduce that in the beginning because this is where we start. Okay. The next thing I want to look at with you is how we can talk about a total change of internal energy. And this is a physics thing. We don't really do much with it in chemistry, but we do want to introduce it. And it's a really simple and straightforward process at the level that we talk about it. So the total change of internal energy, you want to picture internal energy as being the energy possessed by our stuff. So your internal energy can change, and it can change in two different ways. It can change by transferring heat in or out, or it can change by doing work or having work done on it. And in physics, they talk a lot more about work. In here, we talk a lot more about heat. So This is a little bit of a difference of how this works. So I just want to introduce all of this vocabulary to you. We're going to use Q as a variable to represent heat transfer. That lowercase q, not capital Q. Be really careful. We'll use capital Q for something else later. So that lowercase q represents the transfer of heat. And usually we'll have to make sure we're talking about the system or the surroundings. So I wrote this based on the system's perspective. So if the heat transfer is positive, that means that the heat is absorbed by the system. So in the system's perspective, it's gaining heat. Okay, this means, of course, that the thermometer then will record a decrease in temperature because it's going to lose energy to the system. Okay, so from the system's perspective, absorbing heat is a positive Q. From the system's perspective, releasing heat is a negative Q. It's giving off heat to the surroundings. And that means that if we're measuring the surroundings, the temperature of the surroundings will go up. Okay, so you want to always keep that straight. But remember that if Q is positive, heat is absorbed by the system and from the system's perspective. And if the Q for the system is negative, then the heat is released by the system. Okay, so those are things that you need to keep straight. The next thing that I want to look at is work. We use lowercase w to represent work. And work is really, in gases, an expanding and contracting thing. You read about that just a little bit, that if we do work on a sample of gas, we might compress it. So we're pushing it closer together. And I picture that as I'm doing the work, right? And if the gas is expanding the balloon, then it's pushing from the inside out. And I picture that as the gas inside is pushing on the balloon. Okay, so from the system's perspective, if work is done on the system, this means that it's a positive work. Okay, so if W is positive, it means work is done on the system. And if it's a gas, that means that I'm doing work on the system. And if W is negative, this means that work is done by the system. So we have on the system if it's positive and by the system if it's negative. All right. This is a really analogy that's really good for teenagers because, of course, if you have to do work, that's a negative thing, right? So that will help you kind of remember that piece of it. And then it's really, really straightforward and really easy to calculate delta E, the total change in energy, because the total change in energy is just equal to the combination of the heat transfer plus the work transfer. Okay, so the way that you do this is you decide if Q is positive or negative, then you decide if W is positive or negative, and then you add them together. So I'm going to go ahead and do a quick example for you, and we'll do a few of these in class so that you can see this. I want you to see the vocabulary. So a sample of liquid absorbs 13.5 kilojoules of heat and does work equivalent to 1.8 kilojoules when it vaporizes. All right, so vaporizing, of course, is a I must absorb energy kind of scenario to vaporize. So this makes a lot of sense. So I want to calculate delta E, and notice that they wanted in joules, and my work and my heat were given to me in kilojoules. So I'll have to convert that eventually. The hard part about this is knowing the sign. So if the liquid absorbs heat, this means that Q is positive because it's absorbing heat. And if the system does work, that means that work is negative. All right, so now we just put this together. The total change in energy will be equal to positive 13.5 kilojoules because the system is absorbing that heat, plus negative 1.8 kilojoules because the system is doing that work. And when I add those two together, I get positive 11.7 kilojoules, which then, because they want it in joules, I can convert using 1,000 joules per 1 kilojoule to positive 11,700 joules. Excuse me. Get rid of that, make that a little neater. Sorry. Positive 11,700 joules. So it's a pretty straightforward process once you get the hang of it. So the next thing that I want to look at then is about enthalpy versus change in energy, or change in enthalpy versus change in energy. Technically, in physics, there's a big difference because in physics, we're worried about the pressure and the change in volume and the work piece of that, right? But in chemistry, most of our stuff is done at constant pressure in open containers, Or the change in pressure or the change in volume times the pressure is a very small term compared to how much heat energy is actually transferred. So for what we do, we pretty much always assume that the change in enthalpy is equal to the change in energy. And so we're okay with that. And often we'll use that word enthalpy interchangeably with heat energy. Okay, this simplifies our work a lot. So you have a couple different ways that you'll calculate delta H, but I want you to picture that it will always be final minus initial. So the heat energy possessed by the final, the products, minus the heat energy possessed by the initial, the reactants. All right, so what we do, you can use that word heat and enthalpy synonymously, and it should be pretty straightforward. We'll work with it some in class. So now we have to add some more vocabulary, endothermic versus exothermic. So I'll go through endothermic first, and then we'll come back and look at exothermic. And we'll kind of try to remind ourselves that we're talking about the stuff and the energy that the stuff possesses. So our system, all right? So in an endothermic reaction, notice that our stuff in the beginning here at our initial state has less energy than our stuff does at the end in its final state, which means that energy had to be absorbed from the surroundings. So this is an endothermic process. Things that are state of matter changes that are endothermic are melting, boiling, and subliming, where your substance goes from a solid to a liquid to a gas, or from a solid to a gas. But picture that in order to do that, the gas definitely possesses more energy of particle vibration than a solid does, right? Our gas definitely has particles moving everywhere, and our solid is just vibrating. So you want to kind of picture that that's the case. The way that we look at this is that the energy that the stuff possesses increases, so heat has to go in. I want to picture that heat is a reactant. It would be on the left side of the arrow if I were including it there. And when it takes heat in, it takes heat from its surroundings. So the surroundings are losing heat to the system. And this is really important because an endothermic process will feel cold if you're holding it. All right, if you're holding the beaker, the endothermic process will feel cold to you. So that's really important. And endothermic, we give a sign of positive Q or positive delta H. Okay, so this is important, right? We're going to look at exothermic. Notice that an exothermic, where I start, actually has more energy than where I end. So where I end, my stuff has less energy inside than it used to. This means that it had to release energy to the surroundings. This is exothermic. Energy exits my stuff. All right, so the amount of energy that it has decreases. It's going to have to give off heat for that to be the case. So heat would be written on the right side of the arrow if we're writing it in a chemical equation. I'm going to feel warmth when I'm holding it because it's going to be giving heat to me. And because it's losing heat, then we say that delta H or Q would be negative in sign. And our state of matter changes that are exothermic are the process of freezing, liquid turning into a solid, condensing, gas turning into a liquid, or depositing, which is the opposite of sublimation, where a gas would turn straight into a solid. This is kind of weird because we picture that we add cold to water to make it freeze, but remember, we really have to remove heat from water to make it freeze. Okay, so this is an important distinction. You have to be really careful about that. Something that I'm going to keep hammering home is that you pretty much have to collect data with regard to the surroundings, what you're feeling, what's happening on the thermometer, etc. So remember that if the surroundings are gaining heat, that means the system has lost heat. So they do the opposite of each other. And pretty much our data collection is from the surroundings, but we'll always want to be talking about the system. So you have to get used to making that switch. Okay, and because of the law of conservation of energy, we say that the change is equal and opposite in direction. So there's no energy lost anywhere else, which is kind of a fallacy in chemistry because we're going to lose heat to the beaker, we're going to lose heat to the air, we're going to lose heat to the styrofoam, etc. And we won't really be able to calculate that. So we assume that we're not, but It's not really being lost. It's going into the air and everything else, but we just can't calculate it. So just be aware that that is a big source of error in what we do. So I'm getting you ready for this. Thermochemical equations, we've kind of already hinted at. There's some things that are really important about them, and that would be that in a thermochemical equation, we have a true stoichiometric relationship. All right. This means that the coefficients in your chemical equation match the heat in the delta H. Okay, so I would put that in this box at the bottom, that the moles of the substances represented by the coefficients match the amount of heat listed as your delta H. And we call that delta H, if it's part of a thermochemical equation, an enthalpy of reaction or a heat of reaction. And later in the unit, we'll talk about specific types of reactions. And so like formation reactions, we call it heat of formation, or combustion reactions, we call it heat of combustion, etc. So we'll keep using those terms, but in general, the heat of reaction is the delta H that matches your equation as it's written with those coefficients. So picture that in this first equation right here, for every half a mole of O2, and I know that's a kind of a weird thing, we're not used to looking at that, but for every half of a mole of O2, delta H shows that 285 kilojoules of heat are given off. I know it's given off because it's negative, and so that's for every half a mole of O2, but it's also for every 1 mole of H2 and every 1 mole of H2O produced. So they go together, and you have to keep that in mind. This means we can do stoichiometry with this. Okay, so we can write it like I just showed you with the delta H written separately, or we can write it with delta H as a part of the equation, which means you have to remember if it's a reactant, if it's endothermic, the heat has to be written as a reactant, and if it's exothermic, the heat has to be written as a product. All right, so it gets added to either side. It either goes in endothermic reactions or comes out in exothermic reactions. So you can see that this example right here, the heat is on the right side of the arrow. So this is an exothermic reaction. If I wanted to, I could write delta H for that as negative 184.6 kilojoules and leave it out of the equation. So you have to be able to interpret that. In the second equation that I gave you, the 66.2 kilojoules is on the left, so it's an endothermic reaction. And if I were to write delta H separately, it would be positive 66.2 kilojoules. So we're trying to get you used to how all this works, okay? And finally, the last thing that we do is, because heat and enthalpy is a state function, in other words, we don't care how we get to the end. The pathway that we take doesn't make any difference when we're calculating enthalpy. Only how much energy our stuff had in the beginning compared to how much energy our stuff has at the end, where we started and where we end, that comparison. And I always do final minus initial, but that's kind of where we're looking at. So because of that, we can do several different things to our chemical equations and to their delta H's. So our thermochemical equations fit those coefficients and fit the reaction as it's written left to right, etc. But we may have to manipulate that. And Hess's law, Hess gets credit for this. Hess's law is the sum of a bunch of different observations. So the rules that come with this would be that if you need to reverse an equation so that what was the products now becomes the reactants, you're going to change the sign on delta H. That should make sense. If we look at this reaction here, this one, and we see that heat is being given off, if I rewrite this equation so that the reaction goes in reverse, then heat would have to be taken in. All right, so this is the first thing. If you reverse an equation, you change the sign on delta H. If you multiply the coefficients of an equation, you're going to multiply delta H by the same factor. So let's say I'm up here again, and instead of a half a mole of O2, I want this to be 1 mole of O2. That means this would have to be 2 H2s and 2 H2Os. So basically I took my 1/2 times 2, which means I took my H2 times 2 and my water times 2. That means delta H for this reaction with the new coefficients of 2, 1, and 2 would be 285.8 times 2. So negative. All right. So I don't know what that is. Negative 560 something, 570 something. Okay. So about negative 570. not exactly kilojoules. Okay, so picture that that's what we would do if we're going to multiply the coefficients. If you add equations, then you add their delta H's. Okay, so we have three things that we can do. We can reverse the equation, change the sign. We can multiply the equation, multiply delta H, and we can add equations, so we add their delta H's. These are like little puzzles, and you're going to recognize that you need to do this if you're given several different equations or different reactions, and you're asked to find a delta H for an equation that you don't know it for. Usually all of these will be given to you. So the questions look kind of like this. I think they're fun because they're just like little logic puzzles. So this question says that I'm trying to find delta H for this equation. So this is the equation that I want to match. All right. And they give me two other equations to be able to do this. There may be other ways later that we'll talk about how you could find delta H for this, but right now you don't have any other information. So we're given these other two equations, and we want to try to picture how to combine them to give us this equation overall, and then we can mess with their delta H's. So the easiest way to do this is to identify somebody and figure out where they are in the reaction that you want and where they are in the reaction that you see them in already. So I'm going to pick on this N2O5, which is in the products with a coefficient of 1 in the reaction that I want to match, and in the reactants with a coefficient of 1 in the reactions that I was given. So basically, I can use this, but I have to reverse it. Okay, so I'm going to rewrite it as 2NO plus 3/2 O2 yields N2O5. And that will put my N2O5 on the correct side of the equation, right? When I do that, if I'm going to reverse it, I have to change the sign on delta H. So delta H, for the way it's written now in reverse, will still be 223.7 kilojoules. But instead of that being endothermic, it's in reverse now, so it's exothermic. Okay, so I'm going to change the sign. The next thing I'm going to do is look at this and see what else I can identify. So I see that I have two NO2s in what I want to match on the left side. And I have NO2s in what I want to match here on the right side without the coefficient of 2. So I can see that I'm going to have to use this, but I'm going to have to reverse it because I need to switch the side of the arrow that the NO2 is on. And I'm going to have to times it by 2 to give the 2 coefficient to the NO2. So I'm going to go ahead and do that. I'm going to reverse it, which will make this be NO2 yields, I'm going to line up my arrows, it will make it easier, NO plus 1/2 O2, and then I'm going to times it by 2. So this will be 2 NO2, 2 NOs, and 2/2 O2. I can make that 1, but it'll be easier not to, and I'll show you why. Okay, when I do that, I'm going to do my delta H that it was, which was negative 57.1, so reversing it makes it positive 57.1, and times 2, because I had to multiply my coefficients by 2. Okay, I can actually figure out what that is if I want, or I can just write it like that as I'm keeping on. All right, then the last thing I need to do is add them together and see if they give me the equation that I wanted. So my two NOs are on the left and on the right, they will cancel. And I see 3/2 O2 on the left and 2/2 O2 on the right. So that means these guys on the right will go away, and that will leave me with 1 extra half O2 on the left. And that's all that cancels. So this gives me, after I add them together, 2NO2 plus 1/2 O2 yields N2O5. And when I come back up and look at the equation they wanted me to match, that matches the equation. Okay, so because I added those two equations together to get the overall equation, now I'm going to add their delta H's. So negative 223.7 kilojoules plus 2 times positive 57.1 kilojoules comes out to negative 109.5 kilojoules. And so delta H for my overall equation that they wanted me to match up here, calculate delta H, is negative 109, making a mess out of this, sorry, negative 109.5 kilojoules. And that's how you use Hess's law. So we'll play with this in class. Hopefully, you'll find this pretty straightforward, and it's a pretty decent introduction to the vocabulary. I should have covered everything that was in your learning targets with a little bit more detail. So if you need help with anything, make sure that you ask.